March 1972. NASA launches a small probe called Pioneer 10 toward a place nothing built by humans had ever entered. The asteroid belt, the gap between Mars and Jupiter. Nobody knew what was in there. Scientists argued about whether the spacecraft would survive the crossing at all. They launch it anyway. After 7 months inside the belt, it came out the other side, still working. Its detectors never found a single piece of rock bigger than a grain of sand. The most feared place in the solar system was empty. That should be good news. It isn't, because something out of that same empty place wiped out 3/4 of the species on this planet. Both of those things are true. The danger was never that it's crowded. The danger is that it leaks. Tonight, you'll see how a rock escapes, which ones are already on our calendar, and what we found inside the one we caught. Now get yourself comfortable, hit subscribe, we begin. On the morning of February 15th, 2013, at 20 minutes past 9 local time, the sky over southern Russia turned white. Not gradually, instantly. People on their way to work in the city of Chelyabinsk looked up and saw something impossible, a second sun, moving. For a few seconds it burned brighter than the real one. Some of them felt heat on their faces. A few were sunburned. Then the light faded, and for 2.5 minutes, nothing happened at all. The object that caused it was a single rock, roughly 20 meters across, about 65 feet, or the height of a 6-story apartment building. It entered the atmosphere at 19 kilometers per second, which works out to around 69,000 kilometers an hour, or 42,000 miles an hour. To put that into something you can hold in your mind, at that speed, you could cross the Atlantic from London to New York in a little under 5 minutes. It did not survive. Roughly 30 kilometers up, about 19 miles or 3 times the altitude of a cruising passenger jet, the pressure of the air in front of it exceeded the strength of the rock itself, and the rock came apart. The energy released was close to 500 kilotons of TNT, according to the analysis led by Peter Brown and his colleagues, published in Nature. That figure is meaningless until you translate it. 500 kilotons is roughly 30 times the energy of the bomb dropped on Hiroshima. All of it, delivered in a couple of seconds, in the open air above a populated region. And then came the delay, the part almost nobody expects. The flash arrived at the speed of light. The shock wave did not. It took more than 2 minutes to cover the distance to the streets below, which meant that thousands of people, having seen something extraordinary in the sky, walked to their windows to look at it. Think about that for a moment. Picture an ordinary sheet of window glass, the kind in every home you have ever lived in. Now picture it leaving its frame and traveling into the room at the speed of a thrown brick. That is what happened. NASA's assessment records windows blown out across roughly 520 square kilometers, about 200 square miles, an area 5 times the size of central Paris. More than 1,600 people sought medical help, and almost every single injury came from glass. Nobody died. That outcome was luck, not physics. Here is the part that still unsettles the people whose job it is to watch for these things. No telescope on Earth detected that object. Not the night before, not the week before, not ever. It approached from the day side, out of the direction of the sun. Our asteroid surveys work by catching faint reflected sunlight against a dark sky, which means there is one region of the sky they simply cannot look at, the region containing the sun. Try it yourself sometime. Stand outdoors at midday and attempt to spot anything at all near the sun's position. Your eyes refuse. Our telescopes have exactly the same problem, for exactly the same reason, and an asteroid arriving along that line of sight is not merely hard to see. It is hidden inside the light. The rock was invisible until it was already burning. So, the obvious question, what was that thing, and where had it been? We can answer that with unusual precision, because all those dashboard cameras recorded the fireball from dozens of angles, which let researchers reconstruct its path backwards, out of the atmosphere, out past the moon, into the orbit it had held before Earth got in the way. That orbit pointed to one specific region of the solar system, the inner edge of the main asteroid belt between Mars and Jupiter. The fragments recovered from the ice of Lake Chebacool agreed. They turned out to be a stony meteorite of a class called LL chondrite, low iron, low metal, and around 4.5 billion years old, older than the ground you're standing on. Its light-reflecting fingerprint points to a group of asteroids out there called the Flora family. Let's be precise about where that is. Astronomers measure these distances in astronomical units, one astronomical unit being the distance from Earth to the Sun, about 150 million kilometers, or 93 million miles. The belt runs from roughly 2.1 to 3.3 astronomical units. In plain numbers, that is somewhere between 315 million and 495 million kilometers out, between about 200 million and 300 million miles. And now, the contradiction that makes this whole subject so strange. Because if the belt sent us that morning, you would expect the belt to be crowded. It is not. The main asteroid belt is one of the emptiest places we have ever measured. The known objects inside it sit, on average, about 1 million kilometers apart, roughly 600,000 miles. Hold that image properly. The distance from here to the Moon is 384,000 kilometers. So the typical gap between two catalogued asteroids is about 2.5 times the entire Earth-Moon distance. If you were standing on one of them, the nearest neighbor would almost certainly be invisible to your naked eye. The total mass is stranger still. Gather every asteroid in the belt, every boulder, every mountain, every grain of dust, and press it into a single ball, and you would have about 3% of the mass of the Moon. At similar density, that sphere would measure barely 1,000 kilometers across, around 670 miles, less than 1/3 of the Moon's width, and most of that is concentrated in almost nothing. The dwarf planet, Ceres alone, holds something close to 1/3 of the belt's entire mass. Add the next 3 largest bodies, and you have accounted for about 60% of everything out there. Everything else, the entire remainder, is dust, gravel, boulders, and rock. As of May of this year, the Minor Planet Center's catalogue held more than 1.5 million observed small bodies, nearly 900,000 of them with confirmed orbits and permanent numbers. If you counted them off, one every second, without stopping to sleep, you would be counting for more than 17 days. Over 1 million objects, spread across a volume so large they might as well be alone. Films have taught us to picture a churning wall of tumbling debris, spacecraft weaving frantically between boulders. The reality is the opposite. The belt is emptier than any desert on Earth. It is emptier than the cleanest vacuum chamber ever built in a laboratory. Which brings us to a small spacecraft, and a fear that turned out to be wrong. In March of 1972, NASA launched Pioneer 10 toward Jupiter. To get there, it had to pass straight through the belt, and at the time, nobody knew whether that was survivable. The engineers ran the numbers and gave it roughly a 90% chance of getting through undamaged. 1 chance in 10 of losing the mission to a rock nobody could see. Those were the odds they accepted. Now picture yourself aboard. It is July of 1972, and you have just crossed into the belt. You expect something, a shadow, a glint, a sense of arrival. There is nothing. Absolutely nothing. For 7 months you travel through a region 280 million kilometers wide, 175 million miles, and the view never changes. The sun is smaller and colder than you have ever seen it. Every direction is black. The instruments listening for impact stay quiet. Pioneer 10 carried detectors designed to register anything striking the hull or drifting past. Across that entire crossing, they found no particles larger than a single millimeter. Not a boulder, not a pebble, nothing bigger than a coarse grain of sand. It emerged on the far side in February 1973 entirely unharmed. Since then, more than a dozen spacecraft have made the same passage. Voyager, Galileo, Cassini, Rosetta, New Horizons, Juno, and others. Not one has ever been struck by an asteroid. So the belt is safe to fly through. The belt is not safe to live downstream from. And that distinction is the entire subject. Everything we just described is true across a human timescale. Months, years, decades. Across those windows, the belt is empty, quiet, and harmless. Stretch the window to millions of years, and it becomes one of the most violent environments in the solar system, because the collisions never stopped. They have been running without a single pause for 4.5 billion years, since before Earth had oceans, since long before the first living cell. On any given day, nothing happens. Across geological time, everything happens. Every collision produces fragments. Fragments drift, and drifting fragments, given long enough, eventually find the exits. The exits are the strangest feature of the belt, and the most important. At certain specific distances from the Sun, an asteroid's orbital period lines up with Jupiter's in a simple whole number ratio, 2 orbits for Jupiter's 1 or 3 for 1. When that happens, Jupiter's gravity gives the asteroid an identical small tug at the same point, orbit after orbit after orbit. You already know how this works. It is the physics of pushing a child on a swing. Each individual push is gentle and achieves almost nothing, but timed correctly, repeated, the swing climbs until it is out of control. Jupiter has been pushing the same swings for 4.5 billion years. The result is a set of bands in the belt where almost nothing remains, regions we call the Kirkwood gaps. Not gaps in the sense of empty shelves, gaps in the sense of drains. Inside them the motion turns fully chaotic, and an asteroid's orbit stretches from a near circle into a long ellipse. Numerical work by Jack Wisdom and by Alessandro Morbidelli and colleagues showed that the stretch can become extreme in about 1 million years, long enough that the orbit begins crossing the paths of the inner planets or plunges into the Sun. 1 million years sounds like forever. Compress the belt's whole history into a single calendar year, and 1 million years is the last 2 hours of it. Some of the material thrown out of those drains crosses Earth's orbit. Some of it arrives, which is why, at this moment, there is a catalogue. In November of 2025, the European Space Agency announced the discovery of the 40,000th near-Earth asteroid, an object whose orbit brings it within about 45 million kilometres or 28 million miles of our own. 10,000 of those were found in the previous 3 years alone. A quarter of everything we know about our own neighbourhood is knowledge we did not have in 2022. Now, the honest part. Of the objects large enough to devastate a region, 140 metres and up, roughly the height of the Great Pyramid at Giza, current models suggest around 25,000 exist. We have found about 11,500, which means somewhere between half and 60% of the dangerous population has never been seen by anyone. Of the objects we have found, NASA's automated sentry system currently lists close to 2,000, with an impact probability that is not zero within the next 100 years. Almost every one of those numbers sits far below 1%, and almost all of them shrink toward nothing as more observations arrive. This is not a list of threats. It is a list of things not yet ruled out. But one of them briefly broke a record. In December of 2024, a survey telescope in Chile called Atlas picked up a 60-metre object designated 2024 YR4. Over the following weeks, its impact probability for December 22nd, 2032 climbed. 1%, then 2%, then, on February 18th, 2025, 3.1%. One chance in 32. Slightly more likely than throwing double six with a pair of dice. That was the highest impact probability ever formally recorded for an object of that size or larger. Davide Farnocchia at NASA's Center for Near-Earth Object Studies said so plainly at the time, and also said correctly that the record would not last. And there is one more, already scheduled. On the 13th of April 2029, an asteroid called Apophis, 375 meters across, roughly the Empire State Building laid on its side, will pass 31,600 kilometers above the surface of the Earth, 19,600 miles. about 1/12 of the way to the Moon. Our geostationary satellites, the ones relaying weather images and television, orbit at nearly 36,000 kilometers. Apophis will pass beneath them. Roughly 2 billion people will be able to watch it move across the night sky with nothing but their eyes. It will not hit us. We know that with confidence now. But it is coming, it is enormous, and it was manufactured in the same place as the rock that broke Chelyabinsk's windows. So the picture we inherited was wrong, but not in the direction anyone assumed. The belt is not a wall of rock waiting to crush a passing ship. Pioneer 10 proved that with 7 months of silence and a detector that never registered anything bigger than a grain of sand, the danger was never in the crossing. The danger is that the belt is a mill, and it has an output. It is a slow, permanent 4.5 billion year supply line, and Earth sits downstream of it. Nothing on that line is aimed, nothing on it is announced, it simply runs, and every so often something reaches the end, which leaves one question worth everything that follows. If something has been loading that line for 4.5 billion years, what exactly is it made of? Where did all of it come from? And why does the gap between Mars and Jupiter contain the wreckage of what looks unmistakably like a world that was never allowed to finish? That last idea, a shattered world, is not a modern one. Somebody proposed it more than 2 centuries ago, and for a good part of a century, most of the scientific world believed him. To understand why, and to understand why he turned out to be wrong, we have to go back to a time when nobody knew there was anything in that gap at all. Back to when the gap was just a suspicious hole in a sequence of numbers. In 1766, a German mathematician named Johann Daniel Titius noticed something odd about the way the planets are spaced. Not their sizes, not their speeds, their distances. Measured outward from the Sun, the spacing between the planets is not random. Each planet sits roughly twice as far from Mercury's orbit as the one before it. Picture a staircase where every step is wider than the last, and every step doubles, 1 pace, then 2, then 4, then 8. That is essentially what Titius saw. A staircase climbing outward from the Sun in an orderly rhythm. 6 years later, another German astronomer, Johann Elert Bode, published the pattern and made it famous. The rule became known as the Titius-Bode law, and it carried a problem built into it from the beginning. One step was missing. The pattern demanded a planet at about 2.8 times Earth's distance from the Sun, roughly 420 million kilometers out, or 260 million miles, between Mars and Jupiter. Astronomers looked. They found nothing at all. For a while, that was simply an oddity. Then, in 1781, William Herschel discovered Uranus, and Uranus turned up almost exactly where the pattern said an outer planet ought to be, missing the prediction by about 2%. Imagine a map drawn by guesswork that turns out to be accurate to within a few streets. That is roughly the shock the discovery delivered. Suddenly the pattern looked less like numerology and more like law, and if the law was right about Uranus, then something had to be sitting in that gap between Mars and Jupiter. The most famous absence in astronomy had just become a target. In the year 1800, a small group of astronomers decided to stop waiting for luck. They met at an observatory in Lilienthal, a town near Bremen, and formed what they officially called the United Astronomical Society. Among them were Franz Xaver von Zach, Johann Hieronymus Schröter, Carl Ludwig Harding, and a physician astronomer from Bremen named Heinrich Olbers. Informally, they gave themselves a name that has outlived every other detail of the story: the Celestial Police. Their method was almost military in its simplicity. They took the band of sky through which every planet travels, divided it into 24 zones, and wrote to 24 astronomers across Europe, assigning each one a strip to patrol. Think of a search party crossing a field in a line, each person responsible for their own narrow lane, nobody's ground overlapping anybody else's. They were hunting a planet, they had the sky under surveillance, and they were about to be beaten to it entirely by accident, by a man who was not in the group and had never heard of their plan. On the evening of January the 1st, 1801, the first night of the 19th century, a Catholic priest named Giuseppe Piazzi was working at the observatory in Palermo, Sicily. Place yourself beside him for a moment. The room is unheated. Your eye is at the eyepiece of a brass instrument, and your job is tedious to the point of pain. You are checking the recorded positions of stars one by one against an existing catalogue, correcting the errors of earlier observers. Hundreds of nights of this, thousands of stars, and then one of them is in the wrong place. Not dramatically, just slightly. You note it, and you come back the next night, and it has moved again. Stars do not do that. Whatever you are looking at is not a star at all. Piazzi followed it for 41 nights. He watched it creep across roughly 3 degrees of sky, about 6 times the width of the full moon, a distance you could cover with the tip of your thumb held at arm's length. He suspected a comet. He wrote cautious letters. He did not announce a planet. Then 2 things went wrong at once. Piazzi fell seriously ill and could no longer observe, and the object drifted toward the sun's glare into that same blinding region of sky where nothing faint can be seen, the same hiding place that would conceal a rock over Russia 2 centuries later. By the time he recovered, the object was gone. 41 nights of data and a sky full of stars in which it could be anywhere. Here is the problem, and it is worth feeling properly. 41 nights sounds like a lot. Against a full orbit, it is almost nothing, a tiny arc of a path that takes years to complete. Predicting where the object would reappear from that fragment is like being handed one short curved pen stroke and asked to draw the entire circle it came from, perfectly, months in advance. Several of Europe's best astronomers tried. Their answers disagreed with each other by huge margins. And then a 24-year-old mathematician named Carl Friedrich Gauss took the data. Rather than work with the existing methods, he built new ones, techniques for extracting the most probable orbit from imperfect, scattered measurements, the ancestors of the least squares method still used in almost every science today. He produced a prediction that disagreed with everyone else's. He sent it to von Zach. In December of 1801, von Zach pointed a telescope at Gauss's coordinates. The object was there. Olbers confirmed it independently days later. Think about what had just happened. A body lost in the glare of the sun, unseen for most of a year, had been recovered not by searching but by arithmetic. Piazzi named it Ceres, after the Roman goddess of agriculture and the patron deity of Sicily. And for decades afterwards, Ceres was not an asteroid. Ceres was a planet, printed in textbooks, listed in order, sitting between Mars and Jupiter exactly where the pattern had demanded. The gap was filled. The story should have ended there. In March of 1802, Heinrich Olbers found another one, another moving point of light at almost the same distance from the Sun, named Pallas. And this broke everything, because the entire architecture of the solar system, as understood at the time, rested on one unspoken assumption: one orbital zone, one planet. 2 planets sharing the same region was not a small anomaly to be tidied up later. Nothing in any model allowed it. Olbers proposed the solution himself, and it was elegant, dramatic, and completely reasonable given what he knew. A full planet, he suggested, had once occupied that gap, and it had been destroyed. What remained were the pieces. Every prediction that idea made came true. Carl Harding found a 3rd object, Juno, in 1804. Olbers found a 4th, Vesta, in 1807. William Herschel, watching these star-like points that showed no disk at all, coined a new word for them: asteroid, from the Greek for star-shaped. 4 fragments, a shattered world. The theory looked unstoppable. Then the discoveries stopped dead. For 38 years, nobody found another one. Not a single new asteroid between 1807 and 1845. Long enough that the story simply aged out of its own generation. By the time the silence broke, Herschel, Piazzi, von Zach, Harding and Olbers were all dead. The Napoleonic Wars had reached Lilienthal itself. The celestial police had dissolved. Then, In 1845, an amateur named Carl Ludwig Henke found a fifth object, Astrea. After 15 years of patient searching, he found a sixth less than 2 years later, and after that, the discoveries never stopped again. They accelerated instead. By the middle of the century, there were 10 known. Then, in 1891, Max Wolf did something that changed the nature of the work entirely. He pointed a camera at the sky and left the shutter open. On a long exposure photographic plate, a moving asteroid does not appear as a dot. It appears as a short streak. It draws its own evidence while you sleep. A single human eye can only examine one point of sky at a time. A plate examines all of it at once and remembers. By 1900, the count stood at 447, and that curve has been climbing ever since, through the photographic era, through digital detectors, through automated surveys, into the catalogue of well over 1 million small bodies we hold today, which finally gave us enough material to test Olber's shattered world. The exploded planet was not defeated by a single dramatic observation. Nothing so cinematic happened. It was killed by adding things up. The first problem was mass. If you weigh the entire belt, and we can by measuring how its gravity tugs on the orbits of Mars and the inner planets, you get a total of only about 3% of the Moon, not 3% of a planet, 3% of our Moon. A destroyed world would have to have left almost all of itself somewhere else, and no mechanism could hide that much material. The second problem was chemistry, and it was worse. If you shatter one planet, the pieces should be related. Break a fired clay pot, and every fragment is the same clay. But the belt is not one clay. Some asteroids are stony and dry. Some are dark and carbon-rich, holding minerals that only form in the presence of water. Some are dense in metal. They do not read as the pieces of one parent body. They read as objects that formed in genuinely different places, under genuinely different conditions. So the belt is not the wreckage of a world that was destroyed. It is the wreckage of a world that was never allowed to assemble in the first place. And explaining why has produced two competing models that both work, and that scientists have not yet been able to separate. The first is called the Grand Tack, proposed in 2011 by Kevin Walsh, Alessandro Morbidelli, Sean Raymond, David O'Brien, and Avi Mandel. The name comes from sailing. A tack is the maneuver where a boat turns hard and reverses its line across the wind. In this model, Jupiter formed early, in a disk still thick with gas, and gas drags. Jupiter spiraled inward, all the way to about 1.5 times Earth's distance from the Sun, roughly where Mars orbits today. Then Saturn grew, caught up, and the two planets locked into a shared gap in the disk, which flipped the balance of forces acting on them. Jupiter turned around and migrated back out, in and then out, across the asteroid belt region twice. Picture a plough dragged through loose gravel and then dragged back through it again. Almost nothing survives in the furrow. Standard models of the young Sun's disk say the region between Mars and Jupiter should have started with at least an Earth's worth of solid material. What actually remains is less than 1,000th of an Earth mass. For every 2,000 kilograms the models call for, roughly 1 kilogram is left. And the Grand Tack does something else that no earlier model managed. It solves the small Mars problem. Here is that problem, plainly. Mars is small, about 1/10 of Earth's mass. Classical formation models, run honestly, kept producing a Mars nearly as massive as Earth. Every time. Cut the disk short at around Earth's orbit, though, which is exactly what an inward migrating Jupiter would do, and Mars comes out starved and small, just as we find it. One model. 2 stubborn problems solved. But the Grand Tack has a weak joint, and everyone in the field knows where it is. Jupiter's outward migration. Whether a planet's orbit really can expand back out from near Mars to beyond 5 times Earth's distance depends on details of the vanished gas disk that we cannot directly observe, which opened room for a genuinely stranger idea. In 2017, in Science Advances, Sean Raymond and Andre Isidoro published a paper with a title that reads almost like a provocation: The Empty Primordial Asteroid Belt. Their proposal removes the depletion problem by removing the material. What if no planetesimals, no solid building blocks, ever formed between Mars and Jupiter at all? What if that band of the disk was born empty, and everything we now see out there arrived later from somewhere else? And the mechanisms they describe are not exotic. They are unavoidable byproducts of planets forming. From the inside, the rocky planet zone is violent. Bodies growing near Venus, Earth and Mars scatter each other constantly, and some get flung outward, landing in the belt. Those become the stony, dry S-type asteroids that dominate the inner belt. From the outside, Jupiter and Saturn were swallowing gas at enormous rates, and a growing giant destabilizes everything near it. Planetesimals from the region beyond, from Jupiter's neighborhood out past Saturn, were kicked inward, and the surviving gas slowed them just enough to park them in stable orbits. Those become the dark, carbon-rich, water-bearing C-types that dominate the outer belt. Two sources, arriving from opposite directions, sorting themselves by distance. Now, hold both models side by side, because this is the honest position. Both reproduce the belt's tiny mass. Both reproduce how its orbits are spread and tilted. Both reproduce the compositional split, dry inside, wet outside. Neither has been ruled out. Each has one exposed weakness. For the grand tack, it is whether Jupiter could really have sailed back out. For the empty belt, it is the word empty, whether dust in a young disk truly leaves a gap there rather than forming planetesimals everywhere. The most likely way to separate them runs through water. The two models implant C-type asteroids from different source regions, and material from different distances should carry different amounts of it. So the real water content of the carbon-rich asteroids, measured directly from actual returned material rather than inferred from reflected light, may end up deciding which history is ours. That measurement is being made right now. We are not there yet. But notice what both models agree on, because that agreement is the important part. Under either one, the belt is not local debris. Under either one, the objects out there did not all form out there, which reframes the whole region. The belt stops being a graveyard and becomes something closer to a library, a place where material assembled across the entire width of the young solar system ended up filed side by side, sorted roughly by where it came from. Rock from the inner furnace, ice-bearing material from beyond the frost line, all of it parked in the same band, all of it preserved because nothing out there ever grew large enough or hot enough to erase its own history. And that carries an implication worth sitting with. If the outer belt is stocked with material born beyond Jupiter, then some of the objects that later fell to Earth were never inner solar system rocks at all. They only stopped there on the way, including, quite possibly, the one that ended the dinosaurs. But before any of that, there is a more immediate problem, and it comes from the objects themselves. Because when we finally sent spacecraft to the largest bodies in the belt and looked at them closely, not one of them turned out to be a simple rock. Every single one is broken, unfinished, or actively contradicting its own evidence. Begin with the largest, because the largest is also the strangest. Ceres is 940 kilometers across, 585 miles. To feel that properly, a passenger jet flying at ordinary cruising speed would circle its entire equator in a little over 3 hours. The same jet needs nearly 2 days to circle Earth. Small, but not small enough to escape its own gravity. Ceres is round, genuinely round, pulled into a sphere by its own weight, which is why the International Astronomical Union classifies it not as an asteroid, but as a dwarf planet, the only one anywhere inside the orbit of Neptune, and roughly a quarter of it, by weight, is water. Not water on it, water in it. By proportion, Ceres is far wetter than Earth has ever been. NASA's Dawn spacecraft settled into orbit around it in March of 2015, and the first thing it sent back was something nobody could explain. 2 brilliant white patches sitting inside a crater on an otherwise charcoal-dark world. The crater is called a crater, 92 kilometers wide, 57 miles. Now place yourself down there for a moment, standing on the floor of it in a suit. You would never know you were inside a crater at all. On a body this small, the ground curves away sharply beneath you. Your horizon sits barely a kilometer, and a bit away, less than a mile. The rim wall is far beyond it, out of sight entirely. You are standing at the bottom of a hole you cannot perceive. What you could see is the ground beneath your boots, pale, crusted, and about 6 times brighter than the rest of the world around it. Dawn's spectrometers identified the material: sodium carbonate, salt, along with ammonium chloride, and in places hydrated sodium chloride, ordinary table salt still bound to water. And here is the part that changes everything. Salt does not fall from the sky. Salt is what liquid leaves behind when it evaporates. The Dawn team then measured Ceres' gravity field with enough precision to see inside it. Beneath a crater, they found a low-density anomaly, a region where the material is lighter than everything around it, extending tens of kilometers down, several times deeper than the deepest hole humans have ever drilled into our own planet. The interpretation is a reservoir of brine, salty water, kept liquid because dissolved salts drop the freezing point far below zero, the same reason we scatter grit on roads in winter instead of watching them ice over. The story assembles itself from there. An impact, somewhere between a few million and 20 million years ago, punched a crater into the crust and cracked it deeply. Brine found those fractures and rose. At the surface, in near vacuum, the water component flashed away and the salts stayed. That makes Cerealia Facula, the bright patch at the center, something we would not have believed existed on an asteroid 20 years ago. A cryovolcano, a volcano that erupts cold salt water instead of molten rock. And the deposits are young. Analysis of the brightest material puts it at under 2 million years old. When that brine last froze onto the surface of Ceres, our own ancestors were walking the African savanna, chipping flakes off stones to make the first edge tools. Nor is a crater alone. Ahuna Mons, elsewhere on Ceres, is a dome roughly 4 kilometers high, around half the height of Everest, built by pressurized salty water, forced up from below and frozen in place. Then the instruments found something else. Around a crater named Ernutet, Dawn's infrared spectrometer detected organic compounds, long-chain carbon molecules, the kind of chemistry that living systems are built from, though their presence proves nothing about life on its own. The question is where they came from, and scientists genuinely disagree. One camp argues they were made on Ceres. The organics sit alongside carbonates and ammonium-bearing minerals that are unmistakably Ceres' own material. Modelling suggests the volume present is larger than any single impactor could plausibly have delivered, and that the heat of such an impact would have destroyed most of it anyway. The other camp is not convinced. A 2025 analysis using a neural network to comb Dawn's imaging for organic-rich sites argued the global distribution still fits delivery from outside. The debate is live, and it sits on top of 2 others. The first is where Ceres came from at all. Its surface carries ammoniated clays and a great deal of carbon, chemistry that, on the face of it, belongs to the cold outer solar system, not the inner belt, which has led some researchers to argue that Ceres formed far beyond Neptune and was later transported inward. Others point out that the ammonia could have been produced by heating organic matter already present, requiring no journey at all. The source region remains unknown. The second argument is harder and colder. A study published in Science Advances in August of 2025, led by Samuel Courville with Julie Castillo-Rogers at NASA's Jet Propulsion Laboratory, modelled Ceres' thermal and chemical history. Their conclusion: Ceres was most plausibly habitable between about 2.5 and 4 billion years ago, when heat from radioactive decay in its rocky core peaked and warm fluids circulated through the water above. That window has closed. Ceres has no giant planet nearby to knead it with tidal forces the way Jupiter works Europa. The internal heat has faded, much of the water has frozen, and what liquid remains is a cold, concentrated brine. How cold matters enormously. Metabolic activity in life as we know it has generally only been detected down to around -20 degrees Celsius. Ceres' remaining brine sits at or below that floor. So the ingredients are there: water, salts, carbon, and a rocky interior that once ran warm. The conditions almost certainly are not anymore, which is the first version of a pattern you are about to see repeat. Vesta is the second largest body in the belt, 525 kilometers across, about twice the surface area of California, and it holds a distinction nothing else out there can claim. On a clear, dark night, at the right point in its orbit, you can see Vesta with your unaided eye. No telescope, no binoculars. A faint moving point among the stars, 400 million kilometers away. Look at its southern hemisphere, though, and you are looking at a wound. The basin is called Rhea Silvia. It measures about 505 kilometers across, 95% of the width of Vesta itself. Try to hold that. An impact scar almost as wide as the entire body it sits on. Vesta came close to being destroyed outright, and the equator still carries the fracture troughs to prove it. At the center of that basin stands a mountain rising roughly 20 kilometers from the floor, 2.5 times the height of Everest, on a world you could drive across in a few days. Only Olympus Mons on Mars competes with it. That single collision, around 1 billion years ago, blasted about 1% of Vesta into space, creating the Vestoid family of fragments and delivering something to us. Roughly 1 in every 20 meteorites that falls to Earth is a piece of Vesta. Very few objects in the sky can be tied that firmly to rocks in our collections, and those rocks told us what Vesta was: basalt, volcanic rock, which means Vesta once melted through, allowing the heavy metal to sink and the light rock to float, the process that gives a planet a core, a mantle, and a crust. For decades, Vesta was the textbook case, a protoplanet, a world caught mid-formation, layered like Earth but frozen in progress. Then, in April of 2025, that story collapsed. A team led by Ryan Park at JPL published a reanalysis in Nature Astronomy, using nearly a decade of refined calibration on Dawn's radio tracking and imaging data to extract a number nobody had pinned down before: Vesta's moment of inertia. Here is what that means, in plain terms. Moment of inertia describes how an object's mass is arranged around its spin axis, and it is something you have felt in your own body. Hold your arms straight out and spin on a chair. You turn slowly. Pull your arms tight to your chest and you speed up without adding any effort. The mass has not changed. Only where it sits has changed. Bodies with dense cores behave like the tucked-in version. Bodies with mass spread evenly behave like the arms-out version. The scale is beautifully simple. A perfectly uniform ball scores 0.4. Earth, with its enormous iron core, scores about 0.33. Vesta came out at 0.42, essentially uniform. No substantial core at all. Seth Jacobson of Michigan State, a co-author, described the result bluntly. The lack of a core was very surprising, and it leaves 2 candidate explanations, both of which have a flaw sticking out of them. The first, Vesta began differentiating and stopped. The melting and sinking was interrupted before it finished. But Vesta's own meteorites, sitting in laboratories on Earth, show no clear signature of an incomplete process. The second is stranger. Vesta may not be a failed world at all. It may be a fragment, a piece knocked off a larger planet that was still assembling in the early solar system, carrying that planet's crust with it. If that is true, then the meteorite collections in our museums are not samples of something that never became a planet. They are pieces of a planet. We simply do not know which one. Pallas is the 3rd largest, 513 kilometers wide, and its problem is geometry. Nearly everything in the belt orbits in roughly the same flat plane, like cars in lanes on a wide motorway. Pallas does not. Its orbit is tilted almost 35 degrees, which means twice per orbit it dives down through that traffic and back up out of it, crossing every lane at an angle. Nothing about that is gentle. Simulations put its impact speeds above 11 kilometers per second, over 25,000 miles an hour, close to twice the typical collision speed in the belt. Pallas takes 2 to 3 times the cratering that Ceres or Vesta endure. In 2020, a team led by Michael Marset used the Sphere instrument on the European Southern Observatory's Very Large Telescope to resolve its surface for the first time. They counted at least 36 craters wider than 30 kilometers, each one large enough to hold a major city inside it, including a single scar running some 400 kilometers across. Impact craters cover at least a tenth of the entire surface. The team called it the golf ball asteroid. Marset put it more precisely, the most cratered object we know of in the belt. The fourth largest, Hygiea, is nearly spherical, and current thinking is that its roundness is not original. Astronomers suspect it was shattered by a catastrophic collision and then gravitationally reassembled from its own debris, a body that looks whole because it broke and came back together. Then there is Psyche, the largest metal-rich body we know of, and the target of a NASA spacecraft that launched in October of 2023 and arrives in August of 2029. The idea that made it famous was irresistible, an exposed planetary core, a world stripped of its rock, leaving the iron heart behind. The density killed it. Solid iron weighs about 7.8 grams per cubic centimeter. Psyche measures around 4. Take a bucket of Psyche and it weighs roughly half what the same bucket of iron would. A solid metal core is effectively ruled out. 3 possibilities survive and none of them is clean. Psyche could be metal that is around half-empty space, a body so porous it is closer to a metallic sponge than a slab. It could be enstatite chondrite, a stony material that simply looks metallic in reflected light. Or it could be a rocky body that erupted iron onto its own surface, a process sometimes called ferrovolcanism. Its spectra do not settle it either. The surface reads as metal, silicates and hydrated minerals mixed together, and observations with the James Webb Space Telescope found that hydration patchy rather than uniform, which points toward material delivered by impacts rather than welling up from within. Points toward, not proves. 6 years of travel are underway to find out which answer is right. Drop below these bodies, and the nature of the belt changes again. Most asteroids are not rocks. They are rubble piles, collections of gravel, boulders and dust, held together by nothing but their own faint gravity and a little friction. Bennu, Ryugu, Itokawa. Everyone examined up close has turned out to be a loose aggregate with enormous void space inside. Bennu is more than half empty by volume. If you could stand on it, the ground would not resist you. Press a hand into it, and your hand would sink. And they rarely travel alone. In November of 2023, NASA's Lucy spacecraft flew past an 800-meter asteroid called Dinkinesh and found it had a moon, 220 meters wide, later named Selam. Then Lucy looked back as it departed, and the moon was 2 objects resting against each other, a contact binary, the first ever found orbiting another asteroid. 17 months later, on the 20th of April, 2025, Lucy passed Donald Johanson from 960 kilometers out, moving at over 13 kilometers per second, taking an image every 2 seconds. 8 kilometers long, 3.5 wide. 2 lobes fused at a narrow neck, ridged where they meet, a shape the mission team compared to 2 ice cream cones pressed together. Larger than expected, stranger than expected. So look at what the inventory actually says. The round one is a frozen ocean world with cryovolcanoes and a chemistry argument attached to it. The layered one has no core. The tilted one is the most battered surface we know. The fourth is a body reassembled from its own wreckage. The metal one is not metal in any way we understand, and beneath all of them, the population is overwhelmingly loose gravel, often orbiting in pairs, often stuck together in lobes. There is no typical asteroid. Every single category we have examined closely turns out to be an unfinished world, something caught partway through becoming, then stopped. But notice what every one of those descriptions has in common. Okator was punched open, Rhea Silvia nearly split Vesta apart, Pallas is drowning in impact scars, Hygeia is glued together debris, Selam and Donald Johansen are objects that came apart and then reassembled in the wrong shape. Every body out there is a record of being hit, which means none of them is finished being broken. The process that carved every one of these worlds is not history. It is still running, right now, at speeds and on a scale that produces something far more consequential than scenery. Let's be precise about those speeds, because the entire story turns on a single number. When two asteroids meet in the belt, they do not drift into each other. Their orbits are tilted and stretched at slightly different angles, and the difference in their motion averages around 5 kilometers per second. That works out to roughly 18,000 kilometers an hour, about 11,000 miles an hour, 5 times the muzzle velocity of a high-powered rifle. At that speed, the strength of rock stops mattering. Here is why, in terms you can weigh. A single kilogram of asteroid moving at 5 kilometers per second carries about 12.5 megajoules of energy. A kilogram of TNT carries a little over 4. So every kilogram of rock arriving at belt speeds is delivering close to 3 times the punch of the same weight of high explosive. And a boulder does not weigh 1 kilogram. It weighs thousands. Nothing dense at those energies. Nothing chips. Below a certain speed, two bodies touch, crush together and stay, which is how those lobed shapes get made. Above it, they annihilate each other. The parent body ceases to exist and becomes a spreading cloud of its own pieces, and when that happens, the belt keeps the receipt. In 1918, a Japanese astronomer named Kiyotsugu Hirayama did something nobody had thought to do. He took the orbital data for the known asteroids and stripped out the wobble. Every asteroid's orbit is constantly nudged by the planets, so its measured properties shift year to year. But underneath that noise sit deeper values, the average shape, size and tilt of the orbit, which stay almost fixed for tens of millions of years. Astronomers call them proper elements. Think of it as identifying strangers in a crowd not by their clothes, which change daily, but by their height and bone structure, which do not. When Hirayama plotted the asteroids by those permanent values, the crowd was not evenly spread. Groups appeared, dozens of objects sharing almost exactly the same orbital fingerprint, clustered far too tightly for chance. He named them families, and he understood immediately what they had to be. Not neighbors, siblings, the scattered pieces of a single body that had been destroyed. He had never seen a photograph of any of them. He worked it out from columns of numbers on paper. That method still works, and modern computing has industrialized it. In 2024, David Nesvorny and colleagues published a catalogue of proper orbits for 1.25 million main belt asteroids and ran a systematic search for clusters. They found 136 families nobody had identified before. The belt's total now stands at 274. 274 separate catastrophes, each one a body that no longer exists, each one still identifiable by the pattern its debris makes. And they come with dates. Because fragments spread apart at a slow, measurable rate, you can run the motion backwards until the orbits converge, the moment they all shared one point in space. That convergence is the instant of the breakup. The youngest yet found belongs to an object called 1990 SB1. Its family formed roughly 16 to 17,000 years ago. Sit with that. When that asteroid came apart, the last ice age was still gripping the northern hemisphere, and human beings were painting animals onto cave walls in southern France. On any timescale that matters to a geologist, that collision happened this morning. The families that matter most, though, are slightly older, and there is a very specific reason. take the Churning family. It formed when a body about 33 kilometers across shattered in the outer belt, and its age has been pinned down to a precision that borders on the absurd. A 2026 analysis by David Vokrulicki, Nesvorny and William Botka tracked over 2,000 fragments backwards until their orbits converged with the parent body, and dated the event to 5.72 million years ago, give or take about 90,000, roughly the era when the ancestors of chimpanzees and the ancestors of human beings were separating into different lineages, and we can date it to within 100,000 years. Others cluster nearby. The Veritas family formed around 8.3 million years ago. Massalia, roughly 40 million. The Cronus 2 family was long assigned an age of 7.6 million years, but that same 2026 analysis found it difficult to make its largest members converge in that time, suggesting it may need to be older than 10 million. The work is not finished, and some of these breakups are not merely inferred, they are still visible. Infrared telescopes in Earth orbit can detect faint bands of warm dust wrapped around the solar system, tilted at particular angles. Churning and Cronus 2 share exactly the inclination of one such band, the 2.1 degree band, which makes them almost certainly its source. Millions of years after the impact, the smoke has not cleared, but the crucial property of a young family is not its dust, it is the shape of its debris. When a body shatters, it produces far more small fragments than large ones, and for a few tens of millions of years, that ratio stays unusually steep. The family keeps generating an outsized supply of meter-scale rock until collisions and drift grind the distribution back toward the ordinary background. Meter-scale rock is precisely the size that ends up on Earth, which brings us to the question of how anything gets out at all. In 1866, an American astronomer named Daniel Kirkwood was working through the orbits of the few hundred asteroids then known, and he noticed empty ranges, specific distances from the Sun where asteroids simply were not. He also explained them correctly, decades before anyone could demonstrate it mathematically. The gaps sit where an asteroid's year becomes a simple fraction of Jupiter's. At 2.5 astronomical units, about 374 million kilometers from the Sun, or 232 million miles, an asteroid completes exactly 3 orbits for every one Jupiter completes. Further out, at 2.82, the ratio is 5 to 2. At 2.96, 7 to 3. At 3.28, 2 to 1. Now, why should a ratio matter? You already know the answer from an old military rule. Soldiers crossing a bridge are ordered to break step, because footfalls landing in perfect rhythm can drive a structure into oscillations that grow with every stride until something fails. Random footsteps cancel out. Synchronized ones accumulate. Jupiter never breaks step. In those specific bands, the same tug arrives at the same point in the orbit, every single time, for billions of years. What accumulates is eccentricity, a word that simply means how far an orbit departs from a circle. Picture a rubber band held in a loop. Eccentricity is what happens when you pull 2 points of it apart. The loop becomes a long, thin oval. An asteroid on a near-circular orbit stays politely in its lane. Stretch that orbit, and it starts reaching inward across the paths of Mars, Earth, and Venus at one end, and outward toward Jupiter at the other. Inside these resonance bands, the stretching does not proceed gently. A second kind of resonance, a slow one, involving the gradual turning of the orbit's own shape over hundreds of thousands of years, overlaps with the first. 2 resonances layered on top of each other produce genuinely chaotic motion, in the strict mathematical sense. Tiny differences in starting position lead to wildly different outcomes. The eccentricity can climb toward its maximum in about 1 million years, as long ago as our ancestors were first learning to control fire, and then the object is removed. Either it crosses a planet's path and is scattered, or the stretched orbit dips so close to the Sun that it falls in. One more exit guards the belt's inner boundary. Near 2.1 astronomical units sits something called the N6 secular resonance, and it works differently. Nothing about years matching there. Instead, the slow rotation of an asteroid's own orbit falls into step with one of the solar system's fundamental clock rates, and the same relentless accumulation follows. That resonance defines where the belt stops. Cross it, and you do not stay. But every one of these exits shares a limitation. They are narrow, ribbons of instability threaded through an enormous volume of perfectly stable ground. An asteroid sitting safely between two of them will sit there forever, unless something moves it. So what moves it? Sunlight. Not the pressure of the light itself, something far stranger and far more effective. Think about a stone wall that has been in the sun all day. Touch it at noon and it is warm. Touch it at 9 in the evening and it is still warm, hours after the sun has gone, because materials absorb heat and release it slowly. Now, put that stone in space and spin it. The side facing the sun absorbs energy, but the rock does not radiate that heat straight back. It holds it, and by the time it releases it, rotation has carried that patch of surface around to the afternoon side. So the heat leaves the body in a lopsided direction, and because radiation carries momentum, that lopsided emission acts as a thruster, permanently, in one preferred direction. This is the Yarkovsky effect, and until recently we could only model it. Then OSIRIS-REx spent more than 2 years flying alongside Bennu and measured it directly. The force turned out to be equal to the weight of 3 grapes sitting in your palm, about 14 grams, pushing an object 500 meters wide with a mass of roughly 68 million tons. It sounds like nothing. It is not nothing. That push moves Bennu's orbit about 284 meters closer to the Sun every year, which means that over 10 million years, a modest span in this story, the same trivial force shifts the orbit by nearly 3 million kilometers, more than enough to carry a body from stable ground into the edge of a resonance. The first time anyone detected that drift acting on main belt asteroids, incidentally, was in the Karen family, where the fragments are young enough that you can still see how far each one has crept from where it started. So the machine is complete. Collisions make fragments. Sunlight walks the fragments sideways. Resonances catch them and throw them out. Except sunlight does one more thing. The same lopsided emission that pushes an asteroid along also twists it. On an irregular body, heat leaves at slightly different angles from different facets, and the net result is a faint torque, spinning the object gradually faster or gradually slower over millions of years. Astronomers call it YORP, after the 4 researchers who developed the idea, and the consequences are now being caught in the act. During early commissioning observations in April and May of 2025, the Vera C. Rubin Observatory recorded thousands of asteroids in about 10 hours of data, and a team led by Sarah Greenstreet pulled rotation rates out of them. 19 were spinning far faster than they should be. One of them, designated 2025 MN45, is 710 meters across, nearly half a mile, and completes a full rotation every 1.88 minutes. Consider what that means for anything standing on it. A point on its equator is moving at about 70 kilometers an hour, 44 miles an hour, while the surface gravity is so feeble that the outward pull of the spin exceeds it thousands of times over. Loose material could not possibly stay attached. As Greenstreet put it, the object would need cohesive strength comparable to solid rock to hold itself together, which is unexpected because most asteroids are not solid rock at all. For bodies above about 150 meters, there is a well-known limit, sometimes called the spin barrier. Rotate faster than roughly 2.2 hours, and a loosely bound pile should come apart, and some of them do. Spun past the threshold, a rubble pile sheds material from its equator, splits into pieces or throws off debris that settles into orbit around it and becomes a moon, which explains a great deal of what we found in the belt already, and it leads directly into an argument that has not been settled. A small number of asteroids, fewer than a few dozen, do something asteroids should not do. They grow tails, comas of dust streaming behind them on orbits that are unambiguously asteroidal. 2 explanations compete. The first is ice, buried water, exposed by an impact or a landslide, turning straight from solid to vapor and dragging dust off the surface, exactly what makes a comet a comet. Objects behaving this way are called main belt comets. and the case for them is strongest where the activity repeats. Bodies like 133P and 238P have switched on again and again near the same point in their orbits, which is very hard to explain any other way. The second is disruption without any ice at all, an impact that raised a plume, or rotation crossing the barrier we just described, flinging material off the equator. For at least one object, Sheila, the answer is settled, a collision. For others, both explanations still fit the data, and the reason we cannot simply check is frustrating. Direct proof of sublimating ice would be detecting the gas itself, and despite many attempts, no gas has ever been detected coming off any main belt comet. The signal is too faint, so each case has to be argued from indirect evidence, one object at a time. Step back and look at what the belt actually is. Not a ring of ancient survivors sitting undisturbed since the solar system formed. A mill, a machine with an input and an output, running continuously for 4.5 billion years. Bodies collide and shatter. The pieces spread into families we can date. Sunlight walks those pieces slowly outward or inward until they reach a resonance. The resonance stretches their orbits until they can no longer stay. Meanwhile, the same sunlight spins the smaller ones faster and faster until some of them tear themselves apart without being touched at all. The belt has no stable population. It has a turnover, which leaves one question with nowhere else to go. Everything the machine sheds has to end up somewhere, and the exits, by their nature, aim inward, across the orbits of the rocky planets. A fraction of that output arrives here, not occasionally, continuously, and we can prove it because we have been picking the pieces up off the ground for centuries without knowing what we were holding. Go into almost any natural history museum, find the meteorite case, and look at what is sitting there. Usually it is unremarkable. A lump of dark stone, sometimes with a thin black rind, the fusion crust, where the outer millimeter melted on the way down. Often there is a polished cut face, and inside tiny pale spheres embedded in the rock like seeds in bread. Those spheres are chondrules, droplets of molten silicate that froze in space before Earth existed. If you are allowed to lift it, the first thing you notice is weight. Meteorites are denser than they look. A piece the size of a fist can feel like it is trying to pull free of your hand, and every single one of them arrived by the exact process we have just walked through. A parent body shattered. A fragment was walked sideways by sunlight for millions of years. It found a resonance. Jupiter stretched its orbit until it crossed ours. Then it waited, sometimes for millions of years more, until the geometry lined up. The journey takes longer than our species has existed. The arrival takes about 4 seconds. But until very recently, if you had pointed at that rock and asked where in the belt it came from, almost nobody could have told you. Here is the problem, and it is more embarrassing than you might expect. We hold more than 75,000 catalogued meteorites. As of a few years ago, only about 6% of falls had been confidently traced to a specific source. 6 in every 100. Those were the obvious ones. Fragments of the Moon, fragments of Mars, and pieces of Vesta, all identifiable because their chemistry is unmistakable and unique. The other 94%, the overwhelming majority, almost all of them ordinary chondrites, had no address at all. The reason is simple and frustrating. Planets are distinctive. Asteroids are not. Thousands of bodies in the belt reflect light in nearly identical ways, so pointing a spectrograph at a meteorite and then at the belt gives you not one candidate parent, but hundreds. Chemistry alone could not solve it. What finally did was watching the rocks arrive. On the night of the 7th of April, 1959, a fireball crossed the sky over central Czechoslovakia, and for the first time in history cameras were waiting. The Andreev Observatory had a set of widely spaced photographic stations running, all pointed at the sky. Multiple cameras caught the same fireball from different positions on the ground, and when you have 2 or more views of the same object from known locations, you can triangulate the trajectory in 3 dimensions, which means you can run it backwards. Out of the atmosphere, past the Moon, into the orbit, the object had been traveling before Earth interrupted it. 4 stones were recovered near the town of Pshibram. For the first time, we could hold a meteorite in one hand and its own orbit in the other. That single event created an entire discipline. Camera networks spread across Europe, then North America, then Australia, then most of the inhabited world, all sky cameras running every clear night, waiting. And the tally is still small. As of December of 2025, we have 75 recovered meteorites with instrumentally determined pre-impact orbits. 75. Out of more than 75,000 catalogued specimens, roughly 1 in 1,000 rocks in our collections arrived with a return address attached. But 75 turned out to be enough. In 2024, an international team led by Miroslav Broj, Pierre Vernadze, and Michael Marset, working across the CNRS in France, the European Southern Observatory, and Charles University in Prague, combined those orbits with something else. Not chemistry, statistics. They built collisional models of the belt's families, calculated how many meter-sized fragments each one should be producing, tracked how those fragments would drift and escape, and then compared what should be arriving at Earth against what actually lands here. The results came out across 3 papers, in Astronomy and Astrophysics in September, and in Nature in October. Roughly 70% of all known meteorite falls come from 3 recent collisions. Not 3 regions, not 3 broad populations. 3 specific accidents, each involving a body more than 30 kilometers across, and all of them recent. 5.8 million years ago, 7.6 million years ago, and something under 40 million years ago. The breakdown is remarkably clean. Ordinary chondrites come in 3 flavors, distinguished by how much iron and metal they contain: H for high iron, L for low, LL for low iron and low metal. The H chondrites trace to the 2 breakups in the Coronis region. The L chondrites, the single most abundant class in every collection on Earth, trace to Massalia, which alone accounts for something like 37% of known meteorites. The LL chondrites come from the Flora family, and the CM carbonaceous material traces primarily to Veritas. Follow-up work extended the map further, and the origins of more than 90% of meteorites have now been identified. Sit with what that means, because the reframe is larger than it first appears. The meteorite collections of the world, every drawer in every university, every specimen behind every pane of museum glass, every stone that has ever been sliced and analysed, are overwhelmingly the debris of about 4 collisions, none of them older than about 40 million years. Not a survey of the belt, the wreckage of a handful of recent crashes, and the collection is skewed in a second way, which is worse. Ordinary chondrites make up around 80% of falls. They do not make up 80% of the belt. The dark, carbon-rich bodies, the C-complex asteroids, account for more than half of the mass out there. Yet carbonaceous chondrites are just 4.4% of what lands. 2 facts, side by side, that cannot both describe the same reality. So which one is lying? Neither. The gap is real, and the 2024 analysis located it precisely. When the team modelled what is actually approaching Earth at meter sizes, before the atmosphere gets involved, the flux of carbonaceous material turned out to be roughly equal to the flux of ordinary chondrites. Half and half. The difference is made after arrival, in about 8 seconds of atmospheric entry. Carbonaceous chondrite is weak, crumbly, full of water-bearing clays and organic material, with the mechanical integrity of a dried mud brick rather than a stone. Ordinary chondrite is consolidated rock. Hit the atmosphere at 20 kilometers a second, and the difference becomes fatal. The team estimates that either the carbonaceous bodies shatter under pressures around 0.5 megapascal, comparable to the pressure inside a well-inflated bicycle tire, sustained across the entire front face of a falling boulder, or that the heat drives water out of the minerals and cracks them apart from the inside. Which of the 2 dominates is still open. Either way, the filtering is brutal. For the most fragile carbonaceous meteorites, the bias runs to a factor of around 40. For every one that survives to be picked up, Roughly 40 of its equivalents were destroyed on the way in. So, our library is not a census. It is a collection of whatever happened to be tough enough to get through the door, assembled from a few recent accidents, and systematically missing the very material we would most like to study, which is exactly why we started flying out to collect it ourselves. The bodies that matter for all of this are surprisingly small, not the kilometre-scale asteroids. Metre-sized fragments, objects you could park a car beside, are the direct precursors of nearly everything in our collections, and in the source families feeding us, the modelling calibrates their numbers at somewhere between 1 and 2 trillion. That figure resists intuition, so anchor it. Roughly a dozen metre-sized rocks in those families alone, for every human being who has ever lived, across the entire span of our species, waiting, drifting, being walked toward the exits by sunlight. But here is the detail that turns a supply into a system. Once an object escapes the belt and reaches near Earth space, it does not last. Estimates vary, but the typical survival time is only a few million years, brief enough that on the timescale of the solar system it barely registers. 3 endings are available, and every object takes one of them. It strikes a planet, it spirals close enough to the Sun to be destroyed, or a gravitational encounter throws it out of the solar system altogether, which produces an unavoidable conclusion. If near-Earth objects only live a few million years, and the solar system is 4.5 billion years old, then every object out there now must be a recent arrival. The population we track is not ancient. It is being refilled continuously from the belt. Whether any of that reaches the ground comes down to a handful of variables, settled in the last few seconds. Entry angle. A shallow path means a longer journey through thickening air. A steep one means less time to slow down. Velocity, which sets the pressure on the leading face. And above all, what the object is made of. Weak, stony bodies fragment high and dump their energy into the air. Iron bodies, dense, coherent, holding together under enormous stress, punch far deeper and are far more likely to reach the surface intact. And here is what most people misunderstand about impacts. The crater is rarely the danger. The airburst is. When a body breaks apart at altitude, its kinetic energy converts almost instantly into a shock wave, a wall of compressed air spreading outward and downward. That wave does not need to touch the ground to flatten what is standing on it. NASA's current guidance puts the threshold plainly. Space rocks smaller than about 25 meters across will most likely burn up in the atmosphere and cause little or no damage. Below that line, the air wins. Above it, energy starts arriving at the surface, and the Chelyabinsk object sat below the line, around 20 meters, never reaching the ground, and still injured people across an entire city with its shockwave alone. That is what below the threshold actually looks like. So how often does any of this happen? More often than you would guess, and in a distribution that should genuinely unsettle you. More than 100 tons of dust and sand-sized particles enter Earth's atmosphere every single day, roughly the mass of a blue whale arriving continuously, almost all of it as grains finer than the dust on a bookshelf. You have breathed some of it. Objects the size of a car arrive about once a year, producing a spectacular fireball and nothing else. Then the scale climbs. On the 18th of December 2018, an object roughly 10 meters across entered the atmosphere over the Bering Sea at about 32 kilometers per second, 115,000 kilometers an hour, or 71,000 miles an hour. It detonated 26 kilometers up, about 16 miles, releasing 173 kilotons of energy, more than 10 times the Hiroshima bomb. Now consider how we found out. Nobody saw it. No astronomer had it on any list. The blast registered on infrasound stations, a global network of sensors built to listen for covert nuclear tests, which picks up the low, inaudible pressure waves that big explosions push through the atmosphere. 16 of those stations recorded it. American military satellites saw the flash, and the astronomical community learned about it nearly 3 months later, when Peter Brown at Western University in Canada happened to look at the data. Brown's own estimate is that explosions of that energy occur roughly once every 25 years. Above that, the numbers stretch out. An object the size of a football field, the class that leveled 2,000 square kilometers of Siberian forest in 1908, arrives, on NASA's current estimates, every couple of thousand years. Which sounds comfortable until you notice that 2,000 years is shorter than recorded history. And nothing in this pipeline is aimed. No mechanism in the belt selects Earth. Jupiter's resonances do not know we are here. Sunlight pushing on a rotating boulder is not steering. Every step in the chain, collision, drift, resonance, ejection, is blind. And the fraction that intersects our orbit does so purely because our orbit happens to lie in the path of the outflow. Nothing in it is announced either. The largest airburst in 3 decades was detected by nuclear test sensors after the fact over an empty stretch of ocean and passed almost entirely unnoticed by the species it was aimed nowhere near. So the honest way to frame all of this is not as a series of events. Delivery from the belt to Earth is a permanent condition, a background process that has been running since before there was a planet here to receive it, and that has never once paused. Most of what arrives is dust. Some of it is stone. Every so often, on timescales that make human history look like a held breath, something arrives that is large enough to matter. And at least once, something arrived that was large enough to change everything. Not a city, not a forest, the entire biosphere. And for decades, the single most important question about that object, what it actually was, and where in the solar system it came from, could not be answered at all, because the object itself did not survive. It left almost nothing behind. Almost nothing. Go to a roadside cliff in Denmark, or a limestone gorge in Italy, or an exposed hillside in Spain, and you can find what it left. A single dark band running horizontally through the pale rock, usually a centimetre or 2 thick, thinner than your finger. Put your hand on the wall and slide it upward. Below that line, a world with dinosaurs in it. Above the line, a world without. The band shows up on every continent, in seabed cores, in riverbank exposures, always at the same depth in the geological record. Geologists call it the KPG boundary, the seam between the Cretaceous and the Paleogene. And in 1980, Luis and Walter Alvarez discovered what makes that clay different from everything above and below it: iridium. Iridium is a platinum group metal, and it is vanishingly rare in Earth's crust, not because the planet lacks it, but because it bonds readily with iron, and when the young Earth melted and separated, nearly all of it sank into the core. Meteorites, which never went through that process, are comparatively loaded with it. So a worldwide clay layer enriched in iridium and its chemical cousins is not a geological quirk. It is a fingerprint. Something arrived, and it did not survive its own arrival. The object measured somewhere between 10 and 15 kilometers across. Take the middle of that range. A body 12 kilometers wide is taller than Mount Everest is high, and Everest from base to summit is a mountain that takes climbers weeks to ascend and can be seen from 160 kilometers away. Now put that mountain in the sky and give it speed. It struck at roughly 64,000 kilometers an hour, around 40,000 miles an hour, or about 18 kilometers every second. Imagine standing on the shallow tropical shelf that is now the Yucatan Peninsula in the last minute. The object is already inside the atmosphere. From the ground it would look like a second sun swelling in the sky, silent, because it is outrunning its own sound. The air in front of it is compressed so violently it glows brighter than the surface of the sun. Then contact, and the projectile ceases to exist. Not shatters, vaporizes, completely. A mountain of rock converted into superheated gas in less than a second, along with a comparable mass of the seafloor beneath it. The hole left behind is roughly 180 kilometers across, about 110 miles, wide enough that if you placed it over Ireland, it would cover most of the island. Today, you cannot see it. It lies buried under half a kilometer of limestone that has accumulated since, mapped only by gravity surveys and drill cores. And approximately 75% of all species on Earth did not survive what followed. every non-avian dinosaur among them. But here is the strange part. For over 40 years we knew all of that, and we could not say what the object actually was. 3 candidates competed, and the choice mattered enormously. A comet would mean an object from the outer darkness beyond Neptune, arriving on a long, unpredictable orbit, a class of threat we can barely track. An ordinary stony asteroid would mean something from the inner belt, the same population that supplies most of our meteorites. A carbonaceous body would mean something else again, dark, primitive material from the outer edge of the belt or beyond. Each answer implies a different frequency, a different set of dangers, a different picture of what the solar system actually throws at us. In 2007, William Bottke and colleagues proposed an elegant solution. They traced the impactor to the Baptistina family, the debris of a large asteroid that had broken up in the inner belt, which they calculated could have fed fragments into Earth-crossing orbits at exactly the right time. For a few years, the case looked closed. Then the infrared data arrived. NASA's WISE missions surveyed the whole sky in the heat asteroids emit rather than the light they reflect, which gives you their true sizes, and from that, their true reflectivity. When the NEO-WISE team measured over 1,000 Baptistina members, the family's estimated age shifted, landing somewhere in the range of 140 to 320 million years. Too recent for the fragments to have drifted into position in time, and spectroscopic follow-up delivered the second blow. Baptistina turned out to be stony, an S-type family, not the carbonaceous material the boundary layer chemistry implied. The case reopened. Lindley Johnson at NASA put it bluntly at the time: the demise of the dinosaurs was back in the cold case files. What finally cracked it was not dynamics, it was isotopes. Here is the idea, and it is beautifully simple once you see it. Every element comes in slightly different versions called isotopes. Same element, same chemistry, but with different numbers of neutrons in the nucleus, so they weigh slightly different amounts. The proportions of those versions vary depending on where in the original solar nebula the material condensed. And crucially, those proportions never change, not through melting, not through vaporization, not through 66 million years of burial, which means the ratio is a birthmark. Even if the object itself is entirely destroyed, the smear it leaves behind still carries the signature of where it was born. In August of 2024, a team led by Mario Fischer-Goerder at the University of Cologne published in Science. They measured ruthenium isotopes, ruthenium being one of those platinum group metals concentrated in the boundary clay, at 3 kpg sites in Denmark, Italy and Spain. The signatures came out uniform across all 3, and they matched carbonaceous chondrites, which carried 2 conclusions with it. The impactor was a carbonaceous asteroid that formed beyond the orbit of Jupiter, and it was not a comet. After 4 decades of argument, the cometary hypothesis was excluded on chemistry. The same team also ran the test on 5 other impact structures, spanning 36 to 470 million years old. Every one of those 5 came back as a silicate body from the inner solar system, which already told us something uncomfortable. Chicxulub was not a typical impact. It was drawn from a different population than almost everything else that has ever hit us. And then, this month, the identification got sharper and stranger. On the 17th of July 2026, a team led by Georgi Makatadze, working with Frédéric Moynier, Stephen Godris, Philip Claes, and Christian Koberl across the University of British Columbia, the Institut de Physique du Globe de Paris, Brussels and Vienna, published in Science Advances. This time, the element was nickel. 5 isotopes, measured at unprecedented precision, in boundary clay from 5 European sites. The result narrowed the impactor to a specific class, a CO chondrite, formerly an Ornans-type carbonaceous chondrite. Now consider what that means statistically. Carbonaceous chondrites of every kind make up under 5% of meteorite falls. Carbonaceous chondrites are a small fraction of that already small fraction, one of the rarest categories of meteorite anyone has ever picked up off the ground. So the object that ended the Cretaceous was not merely a rock from the belt. It was an unusual rock from an unusual part of the belt, of a type that almost never reaches us. Philippe Claes put it plainly: being hit by such a rare, distant projectile really underscores how unlucky the dinosaurs were. Think about that for a moment. Of all the material the solar system has to throw, the thing that arrived was the thing that almost never arrives. And identifying it did something nobody expected. It undermined the leading explanation for how the extinction actually worked. The dominant model for decades ran on sulfur. The Yucatan target rock is loaded with sulfate minerals. Vaporize a few hundred cubic kilometers of it, add whatever sulfur the impactor itself carried, and you inject an enormous mass of sulfur compounds into the upper atmosphere. Those form fine aerosols that reflect sunlight, the same mechanism that cools the planet for a year or two after a large volcanic eruption, only scaled to something monstrous. But carbonaceous chondrites are dry. They are notably poor in the volatile elements: carbon, zinc, water, and above all sulfur. The new analysis suggests the impactor delivered only about half the sulfur that earlier models assumed, which does not remove the sulfur mechanism. It weakens it and shifts weight onto something else. Dust. Not dust from the asteroid. Dust from the target, Earth's own crust, pulverized by the impact and blown into the stratosphere. In 2023, a team led by Sem Burke-Senel at the Royal Observatory of Belgium published paleoclimate simulations in Nature Geoscience, built on grain-size measurements from an exceptionally well-preserved boundary deposit in North Dakota. What they found in that sediment was a far larger proportion of very fine particles than anyone had expected, silicate grains in the range of roughly 1 to 8 micrometers. Micrometer-scale dust behaves nothing like the dust you sweep off a floor. You have watched this happen. Throw a handful of sand into still air and it drops immediately. Disturb a fine talcum powder in a shaft of sunlight, and the particles hang there, drifting, seemingly refusing to fall. Below a certain size, air resistance overwhelms weight, and a particle stops settling in any practical sense. The simulations suggest that plume could have remained aloft for around 15 years, driving global average surface temperatures down by as much as 15 degrees Celsius, 27 degrees Fahrenheit, and shutting down photosynthesis almost entirely for close to 2 years. 2 years without photosynthesis. Every food web on the planet begins with something converting sunlight into sugar. Remove that first step, and the collapse runs upward through every level above it, on land and in the ocean. Not fire, not the blast, not the tsunami. Starvation in the dark for a very long time. But the argument is not finished, and honesty demands saying so. Sulfur and soot from global wildfires still contribute in every serious model. The question is proportion, not presence. And a much older debate remains genuinely live: the Deccan traps. At almost exactly the same period, one of the largest volcanic provinces in Earth's history was erupting across what is now Western India, flooding hundreds of thousands of square kilometers with lava and venting enormous volumes of gas into the atmosphere over hundreds of thousands of years. Some researchers argue the Deccan eruptions had already destabilized the biosphere and that the impact struck an ecosystem under stress. Others argue the extinction pattern is far too abrupt for volcanism to be the driver, and that the impact alone accounts for it. The disagreement is unresolved, and it is not a fringe dispute. Which of those two forces did the primary work, or how the two combined, remains one of the genuinely open questions in Earth science. The record holds a second event we can examine, and it is far smaller and far closer. On the morning of the 30th of June, 1908, something detonated in the sky above the Podkamennaya Tunguska River in central Siberia. The blast flattened roughly 2,000 square kilometers of forest, around 800 square miles, an area larger than Greater London. An estimated 80 million trees went down, splayed outward from a central point like spokes. Seismographs registered it across Eurasia. Barometers in England picked up the pressure wave. For several nights afterwards, the skies over Europe glowed brightly enough that people reported reading newspapers outdoors at midnight, and no scientific expedition reached the site until 1927, 19 years later, when Leonid Kulik finally arrived expecting a crater. He found no crater. He still found the forest, flattened to the horizon in every direction. Much about Tunguska remains argued. The energy estimates are reconstructed indirectly from the extent of the destruction and the seismic records, and published values span from a few megatons to a few tens, with 10 to 15 most commonly quoted. The object's size, its burst altitude, and even whether it was stony or icy are still not settled. A proposal that a small lake near the epicenter, Lake Checo, is an impact crater from a surviving fragment has been largely rejected. Sediment cores suggest the lake predates 1908, though the case is not formally closed. What is not disputed is the death toll. No confirmed fatalities. Not because the object was gentle, because of where on the planet it happened. Rotate the Earth a few hours and the same object arrives over a European capital. And that raises the obvious question. If events like these happen, where is the rest of the evidence? Earth destroys it. Rain, wind, and ice grind craters down. Vegetation swallows them. Plate tectonics recycles entire sections of crust into the mantle. And roughly 70% of the surface is ocean, where an impact leaves a scar on a seafloor that will itself be subducted within a couple of 100 million years. Our planet is not an archive. It is a machine for forgetting. The moon is the archive. No air, no water, no tectonics. Every scar it has taken across 4 billion years is still sitting there, visible tonight through an ordinary pair of binoculars. And here is the sobering part. The moon and the Earth occupy the same neighborhood, sweeping through the same debris. Earth is larger and gravitationally stronger, so it caught more, not less. Every one of those great dark basins you can see with your unaided eye had a terrestrial counterpart. We simply do not have them anymore. So how often does this happen? The honest answer scales steeply with size, and the numbers are worth laying out in order. Objects around 10 meters across, the Bering Sea class, arrive every decade or two, releasing tens to hundreds of kilotons, almost always over ocean or empty ground. Objects of a few tens of meters, the Tunguska class, arrive on timescales of centuries to a few thousand years, depending on the model you trust. Objects around 140 meters, large enough to devastate a region rather than a forest, arrive on the order of once every few tens of thousands of years. Kilometer-scale impacts, the ones with global climatic consequences, fall somewhere between 100,000 and 1 million years apart. And Chicxulub-scale events, 10 kilometers and up, separate by something on the order of 100 million years, possibly considerably longer. Look at that ladder and notice the trap built into it. Every interval on it is longer than any human institution has ever survived, longer than any civilization. For the events that could actually end us, the recurrence time exceeds the entire span of recorded history by orders of magnitude. The threat is real, and it is slow. And slow is precisely what makes something easy to ignore, because nothing in our biology or our politics is built to take seriously a danger that arrives on a schedule nobody alive will ever see. Every previous species on this planet faced exactly that problem and had no way even to perceive it. But something changed. For the first time in 4.5 billion years, the planet has an early warning system, telescopes on mountaintops, automated software recomputing orbits every night, and a small number of people whose entire job is to find the next one before it finds us. The question is no longer whether the belt can reach us. We have settled that. The question is whether watching is enough. Watching began by accident on the 13th of August, 1898. That night, Carl Gustav Witt at the Urania Observatory in Berlin photographed a long exposure of the sky and found a short streak where a point of light should have been, an object moving fast enough to smear across the plate. On the very same night in Nice, Auguste Charlois independently recorded the same object. They had found Eros, the first near-Earth asteroid ever discovered, a rock that does not stay politely out beyond Mars, but comes in close enough to matter. And after that first find, almost nothing happened for a very long time. By 1980, 82 years later, the total catalogue of known near-Earth asteroids stood at 44 objects, roughly one discovery every 2 years, and nearly every one of them stumbled across rather than sought. We were not watching, we were occasionally noticing. That changed when the finding became deliberate, and then it changed again when it became law. In 2005, the United States Congress directed NASA to find and catalogue 90% of near-Earth objects larger than 140 meters, the size class capable of destroying a region rather than a city. 21 years have passed. The target has not been met. Something under half of that population is known, which means the majority of the objects the mandate was written about have still never been seen by anyone. But the machinery built to chase it is genuinely extraordinary and worth understanding because it never stops running. 2 automated systems sit at the center of it, both operated by NASA's Center for Near-Earth Object Studies at the Jet Propulsion Laboratory. They do different jobs. Sentry takes the entire catalogue of known asteroids and continuously searches every one of their possible future paths for collisions with Earth over the next 100 years. Not once, continuously, recomputing as each new observation arrives, adding objects, removing them, without pause. Scout handles the opposite problem. When a survey telescope reports something brand new with only a few hours of data, the orbit is barely constrained at all. Scout takes that thin, unreliable arc and estimates whether the object could hit anything in the coming days. Sentry is the long-range radar. Scout is the smoke alarm. And because raw probabilities communicate almost nothing to people who do not work with them, 2 scales exist to translate. The Torino scale runs from 0 to 10, combining probability and energy into a single number, the way hurricane categories compress wind speed and pressure into something a person can act on. The Palermo scale does something subtler. It compares a specific predicted event against the ordinary background risk of an impact that size happening by chance in the same window. A negative Palermo value means the threat is less than the noise we already live inside. All of this ran quietly for 2 decades. Then, one object put the entire system to the test. On the 27th of December, 2024, the Atlas Survey Telescope at Rio Hurtado in Chile picked up a faint moving point of light. It received the designation 2024YR4, and when astronomers worked out its trajectory, they discovered something uncomfortable about the timing. The object's closest approach to Earth had already happened. 2 days earlier, on Christmas Day. We did not detect it coming. We detected it leaving, because it had approached from the day side, buried in the direction of the sun, and only became visible once it had passed us, and was climbing away into the dark. Then the numbers started moving. Over the following weeks, the calculated probability of an Earth impact on the 22nd of December, 2032 rose steadily, through 1%, past 2%, and on the 18th of February, 2025, to the highest figure ever formally recorded for an object that size or larger. For the first time, the international coordination arrangements built for exactly this scenario were not a tabletop exercise. Observatories across the world reprioritized. Space agencies opened communication channels. A rock roughly the width of a football pitch had made every one of those procedures real. The resolution came from above the atmosphere. The James Webb Space Telescope observed it in March of 2025, and its mid-infrared measurements settled the size, 60 meters across, give or take 7. Not the 200-meter monster some early estimates allowed for, but still a body capable of leveling a metropolitan area. More importantly, the improved orbit eliminated the Earth impact entirely, and then something happened that nobody had scripted. The risk did not disappear. It moved. As the uncertainty region shrank, Earth fell outside it. but the Moon did not. The probability of a lunar impact on that same December date began climbing instead. By the end of the observing window in May of 2025, it stood at around 4.3%. Roughly one chance in 23 that a 60-meter asteroid would strike the Moon on a date we could name. And then we lost it. By April of 2025, the object had receded so far that no telescope on the ground could see it. The working assumption was that we would have to wait until 2028 for another look, which meant sitting with an open 4% question for 3 years. Except astronomers found 2 narrow windows. In February of this year, on the 18th and again on the 26th, Webb turned its near-infrared camera on a patch of sky where the asteroid should have been. Understand what that means, because the difficulty is almost absurd. By then, the object was 4 billion times fainter than anything the human eye can perceive. Jan de Wit and Andrew Rivkin, who led the analysis, described the brightness in a way that lands properly. It was reflecting about as much light as a single almond would, if you place that almond at the distance of the Moon. 20 to 30 times fainter than the smallest asteroids other observatories can reach. And the team did something clever with the timing. They chose their exposures for moments when the asteroid would drift close to specific background stars. Stars whose positions the European Space Agency's Gaia mission had already mapped to extraordinary precision, which turned those stars into survey markers. With the asteroid and the reference points in the same frame at the same instant, its position could be pinned down far more tightly than ever before. The uncertainty in where it would be in 2032 narrowed by roughly a factor of 12. On the 5th of March, 2026, 5 months ago, NASA announced the result. The lunar impact is ruled out. Asteroid 2024 YR4 will pass the Moon at a distance of about 21,200 kilometers, 13,200 miles. Earth impacts across the next century, eliminated as well. The Moon is safe, and that sentence turns out to matter far more than it sounds, because a strike on the Moon would have been our problem too. Work published in 2025 by Paul Wiegert, Peter Brown, and colleagues at the University of Western Ontario modelled what a 60-metre impact on the lunar surface would actually do. No danger to anyone standing on Earth. The atmosphere shields us completely. The danger sits above the atmosphere. An impact that size would excavate a kilometre-scale melt pool, trigger a moonquake detectable across the entire Moon, and throw a cloud of rock off the surface. Some of that debris would exceed lunar escape velocity, and depending on exactly where the strike landed, a significant fraction could arrive in near-Earth space within days. The modelling suggests the meteoroid flux around Earth could run 10 to 1,000 times above normal background for a few days. The particles would travel at roughly 10 kilometers per second, slower than typical meteors, but still around 11 times the speed of a rifle bullet. The researchers estimate that across the entire satellite fleet, as it will exist in 2032, that would mean thousands to tens of thousands of millimeter-scale impacts, individually survivable for most spacecraft. Collectively, the equivalent of years to a decade of normal exposure delivered in about 72 hours, plus a meteor storm in the sky over your head, running at possibly hundreds of fireballs an hour. So a rock too small to threaten the ground, hitting a body 250,000 miles away, could have damaged a substantial fraction of the infrastructure that civilization now runs on. That is how thin the margins have become, and it is why the watching matters even for objects that will never touch us. The most precisely tracked asteroid in existence is Bennu, because we sent a spacecraft to fly alongside it for over 2 years. Davide Farnocchia's team at JPL used that tracking to pin Bennu's distance from Earth to within about 2 meters at dozens of separate moments. 2 meters across tens of millions of kilometers. That precision brought us a specific date, the 24th of September, 2182, the single most significant impact possibility for Bennu, at a probability of roughly 1 in 2,700. But the interesting part is what that number depends on. In 2135, Bennu will pass between the Earth and the Moon. That encounter is safe, no chance of collision. What it does is bend Bennu's orbit, and how much it bends depends on exactly where in that flyby the asteroid crosses. Scattered through that approach are regions astronomers call gravitational keyholes. A keyhole is a narrow window in space, some only a few meters wide, others up to a couple of dozen kilometers, where Earth's gravity would deflect the asteroid onto a path that returns for a collision generations later. Miss every keyhole, and Bennu is harmless indefinitely. Thread 1, and a date in the 22nd century becomes real. Analysts originally identified 26 candidate keyholes. The OSIRIS-REx tracking eliminated all but 2. And what decides which side of those 2 windows Bennu passes on is not gravity. It is the faint thermal push of sunlight on a rotating rock, accumulating over a century and a half. A force you could hold in one hand, deciding a planetary outcome 150 years from now. Which brings us to something far closer and far larger. In April of 2029, Apophis passes beneath our satellites, an event already covered by every planetary defense program on Earth. But the reason it matters scientifically is not the near miss. It is what Earth will do to Apophis. Passing that close, our gravity will pull unevenly across the asteroid's body, stronger on the near side than the far side. That differential stretching is what we call a tide, and on a loosely bound rubble pile, it may be enough to trigger landslides across the surface, shift boulders, and expose subsurface material that has never been touched by sunlight or the solar wind. Fresh, unweathered asteroid interior, revealed by our own gravity, in real time. And for the first time in history, we will be there to watch it happen. NASA has redirected the spacecraft that returned the Bennu sample, now renamed OSIRIS-APEX, to arrive after the flyby. The European Space Agency is developing Ramses to be in position before it, before and after, a controlled experiment on a real asteroid run by the Earth itself, but all of that is observation. The harder question is whether we could do anything. On the 26th of September, 2022, we found out. A spacecraft weighing around 570 kilograms, roughly the mass of a vending machine, struck a 160-meter asteroid called Dimorphos at just over 6 kilometers per second, about 14,000 miles an hour. The mission was DART, and it was deliberately destroyed on contact. Dimorphos orbits a larger asteroid, Didymos, which made the test measurable, changed the orbit and the timing changes, and telescopes on Earth can see the difference. The prediction, if all the spacecraft's momentum transferred straight into the rock, was a shortening of about 7 minutes. The measured result was 33 minutes. Its orbital period dropped from 11 hours and 55 minutes to 11 hours and 22, roughly 25 times the minimum threshold the mission had set for success. Why so much more than predicted? Because the impact threw material off the asteroid, and that material carried momentum away in the opposite direction. The debris plume stretched more than 10,000 kilometers into space and persisted for months. 37-meter scale boulders were flung clear of the asteroid entirely. Every kilogram leaving pushed back. The asteroid was not merely shoved. Briefly, it became a rocket, and the ejector carried more momentum than the spacecraft that started it, which is where the honest uncertainty begins. The efficiency of that momentum transfer is captured in a single number, and we cannot yet pin it down. Current bounds put it somewhere between roughly 2 and 5, meaning the impact delivered between 2 and 5 times the punch of the spacecraft alone. A factor of 2 might sound like a technicality. It is not. That range is the difference between a deflection mission needing to launch 5 years before a predicted impact and needing to launch 10. And the reason we cannot narrow it is simple. We do not know Dimorphos's mass. Momentum efficiency is a ratio, and one side of that ratio is missing. There is a second surprise waiting as well. Simulations run with the burn impact code suggest DART did not excavate a crater at all. On a body that loosely bound, closer to a pile of gravel than a rock, the impact may have deformed the entire asteroid, reshaping it globally rather than punching a hole in it. If that is right, then our one real-world test of planetary defense worked for reasons we did not fully anticipate on a target far weaker than assumed. The European Space Agency's Hera spacecraft launched in October of 2024 and arrives at the system later this year, carrying instruments and 2 small CubeSats to measure Dimorphos's mass, map what DART left behind, and finally close that gap. The answer is not in yet. It is a few months away. So, can we do anything? Yes. Demonstrably, measurably yes. A half-ton spacecraft moved a mountain, and it moved it far more than anyone expected. But notice the condition buried inside that success. Every deflection method we have and every one we might build works by nudging, by applying a small change very early, and letting orbital mechanics amplify it across years of travel. Which means the entire capability rests on warning time, and warning time rests on the catalogue. For something like Apophis, tracked for decades, we would have generations of notice. For something like 2024 YR4, detected 2 days after it had already passed, we would have had 7 years. Enough, but only barely, and only by luck. And for the majority of the dangerous population that no telescope has ever recorded, the warning time is not measured in years. It is whatever we get between detection and arrival. We can defend ourselves against what we can see. That is the whole of it. But something else came out of all this. Something nobody was looking for when the missions were designed. Because we did not only go out to those asteroids to measure their orbits. On one of them, we landed, took a handful of material and brought it home. And what was inside that handful had almost nothing to do with planetary defense. On the 24th of September 2023, a capsule came down over the Utah desert. It had been released 7 years after launch from a spacecraft that never entered Earth's atmosphere itself. Recovery teams reached it within hours, sealed it, and flew it to a clean room at NASA's Johnson Space Center, where the container was opened under conditions designed to keep our own world out. Inside sat 121.6 grams of asteroid Bennu, less than the weight of a baseball, dark grey, powdery, with fragments up to a few centimeters across. If you held it in your palm, you would not think twice about it, and Bennu is not even a primary object. It is debris, a fragment broken off a much larger parent body, possibly as long as 2 billion years ago, and later delivered inward. A piece of a ruin. What that handful contained has quietly rearranged one of the oldest questions we have. The first measurement was bulk carbon, and it came in at 4.5% by weight, with roughly 90% of that locked inside organic molecules. For every kilogram of Bennu, about 45 grams is carbon. That is higher than the samples returned from the asteroid Ryugu, and higher than any carbonaceous meteorite previously studied, which changes how you should picture the thing. Bennu is not a rock with traces of carbon in it. Bennu is closer to a rock made partly of soot and tar, and the tar is the interesting part. Analysis of the organic fraction identified around 16,000 distinct molecular formulae, built from carbon, hydrogen, nitrogen, oxygen, sulfur, and magnesium. 16,000 different chemical recipes in a sample smaller than a fist. Then researchers looked for specific molecules, and they found the ones you would only expect on a living world. 33 amino acids, the units from which proteins are assembled. 14 of those 33 are among the 20 that terrestrial life uses to build every protein in every organism on Earth. Glycine, the simplest, was the most abundant. The other 19 are amino acids that biology here barely uses or does not use at all. And then the genetic letters, all 5 nuclear bases: adenine, guanine, cytosine, thymine, and uracil. The complete set of characters that DNA and RNA are written in, present in an asteroid fragment that has never been alive. In November of 2025, a team led by Angel Majaro at NASA's Goddard Space Flight Center published one more result in Proceedings of the National Academy of Sciences, and it is worth stating carefully because the team themselves were careful. Across multiple replicate portions of the sample, they found trace signals consistent with tryptophan. They described the detection as tentative, not confirmed. But if it holds, tryptophan would be the 15th protein-building amino acid identified on Bennu, and the first time anyone has found it in extraterrestrial material. And notice why it might never have shown up before. Tryptophan is fragile. Mojaro's team point out that a delicate fraction of organic molecules in meteorites may simply not survive the heat of atmospheric entry, which means the reason we had never seen it is not that asteroids lack it. The reason is that the atmosphere destroys it, and this time we went and collected the material before the atmosphere could. The team draw one further conclusion, and it is a quietly sobering one. If tryptophan forms naturally inside asteroids, then finding tryptophan somewhere cannot be treated as proof of life. One of our biosignatures just became less reliable, but the organics are not the most remarkable thing in the sample. The salts are. In January of 2025, a team led by Tim McCoy at the Smithsonian's National Museum of Natural History published in Nature what they found in the inorganic fraction: sodium-bearing phosphates and sodium-rich carbonates, sulfates, chlorides, and fluorides. Together, those minerals form what geologists call an evaporate sequence. You have seen an evaporate. Leave a glass of salty water on a windowsill and come back in a week. A white crust at the bottom. That crust is the salts the water was carrying, left behind in a specific order as the water disappeared. The least soluble first, the most soluble last. The sequence encodes the drying. Scientists have found individual evaporate minerals in meteorites before. Nobody had ever found a complete set, one that preserves the whole process, an evaporation that may have run for thousands of years or longer. Some of the minerals had never been identified in any extraterrestrial sample at all. Among them, trona, a sodium carbonate that on Earth forms in dried-out sodium-rich lake beds, like Searles Lake in the Mojave. So place yourself inside Bennu's parent body 4.5 billion years ago, not on its surface, inside it, in the dark, in a crack in the rock. Radioactive decay has warmed the interior enough to melt the ice, and now there is standing liquid water in the fractures, shallow, muddy, saturated with dissolved salts. McCoy described what a glass of it would have been like to drink, tepid and salty. Not appealing, but warm, wet, mineral-rich and stable for a very long time. And then the two reagents. The samples contained exceptionally high concentrations of ammonia. They also contained formaldehyde. Put those two compounds together under the right conditions and they react, assembling into amino acids. Read that back. Inside the same body, at the same time. Liquid water, dissolved salts, ammonia, formaldehyde, and the products those reactions make, not the ingredients scattered across the solar system. The ingredients, the reagents, and the reaction vessel in one place. Let me be completely clear about what this does not show. Nothing in the Bennu sample indicates that life ever existed there. No cells, no structures, no metabolic signatures. What existed was the chemistry and the environment for the chemistry to run in. And one detail keeps that gap honest. Many amino acids come in two mirror image forms, like a left and a right hand. Life on Earth uses almost exclusively the left-handed version. The Bennu sample contains an equal mixture of both, which means whatever made biology choose one hand did not happen out there. It happened here or on the way. If Bennu's parent body were unique, this would be a curiosity. The evidence says otherwise. Brines closely comparable to what those salts record have been inferred at Ceres, and detected directly, streaming into space in the plumes of Saturn's moon Enceladus, which suggests the pattern generalizes. Not one lucky rock, but a standard condition of small icy bodies in the early solar system, warm, salty water running through fractured rock, cooking prebiotic chemistry for millions of years, everywhere. The building blocks were not rare, they may have been ordinary, which raises the older question that has never been settled. Earth almost certainly formed too close to the Sun for water ice to survive, so the water in your body arrived from somewhere further out. The argument is over what carried it. The evidence runs on deuterium, a heavier form of hydrogen with an extra neutron. The ratio of deuterium to ordinary hydrogen in water depends on how cold it was where that water formed, and the ratio is essentially permanent. A fingerprint. Earth's seawater has a specific value, and carbonaceous chondrites, particularly the Ci and Cm classes, match it closely. Comets, for a long time, did not. The Oort cloud comets measured so far run at roughly twice the terrestrial ratio, which appeared to rule them out as the main source. Except comets turned out to be more varied than anyone expected. When the Herschel Space Observatory measured the Jupiter family comet Hartley 2, its ratio came out consistent with Earth's seawater. Then Rosetta measured comet 67P and found roughly 3 times the terrestrial value. So the two families overlap, and neither is a single population with a single answer. Recent work suggests something more complicated still, that Earth's volatiles were sourced heterogeneously from at least 2 separate reservoirs of water that mixed within the disk, which does not so much resolve the debate as dissolve the question it was built on. The honest position: carbonaceous asteroids remain the strongest single candidate, and the picture is almost certainly not that simple, and the belt keeps offering complications. Astronomers have reported water ice on the surface of the asteroid Themis, which should be impossible. A widespread thin frost at that distance from the Sun would sublimate away far faster than the observational limits allow. So either the ice is confined to small, clean, permanently shadowed patches, or impacts keep excavating buried ice and re-exposing it every few thousand years. Nobody has settled which. What we can say is that Ceres holds roughly a quarter of its mass as water, making it the wettest known body in the inner solar system, and that it is now treated seriously as a relict ocean world and a serious candidate for a future sample return. And somewhere in the last decade, the conversation shifted. Once you describe the belt as a repository of metal, water, and volatiles, someone will describe it as inventory. Metal-rich asteroids have been reframed as ore bodies, and the numbers attached to them are spectacular. Psyche, in particular, has been valued in headlines at $10 quintillion, or 10 quadrillion, depending on which article you read, which tells you most of what you need to know about the rigor involved. Those figures come from multiplying an estimated bulk composition by today's commodity prices, and that calculation contains a flaw so large it collapses on contact. Consider what actually happens if you deliver a mountain of platinum to Earth. Platinum is expensive because it is scarce. Remove the scarcity, and you have not created $10 quintillion of wealth. You have destroyed the price. The valuation assumes a market that cannot survive the delivery. Meanwhile, the practical state of play is modest. No private spacecraft has yet landed on an asteroid anywhere outside the Earth-Moon system, and the plausible first product is not a precious metal at all. It is water, because water splits into hydrogen and oxygen, which is rocket propellant, and propellant is the single heaviest thing we launch. Every kilogram lifted out of Earth's gravity costs enormously. A kilogram already in space costs nothing to have got there. The economics only close if you never have to lift it in the first place, which is a strange and rather beautiful inversion. Not gold, not platinum. Water, the same substance whose delivery to Earth we cannot yet fully explain. Except one thing is missing entirely, and it is not technical. No international framework governs the ownership or the environmental protection of asteroid resources. The Outer Space Treaty of 1967 forbids any nation from appropriating a celestial body. Whether that forbids extracting material from one is genuinely contested among legal scholars. Some argue extraction inevitably creates the exclusive rights the treaty prohibits. Others that using resources differs from claiming territory. Individual nations have passed their own conflicting laws in the gap, and the gap is widening because the capability is accelerating. The Vera C. Rubin Observatory, still not in full survey mode, took about 1 million observations across roughly 6 weeks and produced over 11,000 new asteroid discoveries, the largest single batch submitted to the Minor Planet Center in a year. Once fully operational, it is expected to add nearly 90,000 new near-Earth objects and to lift the census of those larger than 140 meters from around 40% to something near 70. And in September of next year, at the earliest, NEO Surveyor launches, the first space telescope ever built for no purpose but this. Led by Amy Mainzer at UCLA, it carries a single instrument, a 50-centimeter infrared telescope, about 20 inches across. Infrared, because that is the honest answer to the problem this entire story has circled. The most dangerous asteroids are as dark as charcoal. In reflected light, they are nearly invisible. But every one of them absorbs sunlight and re-radiates it as heat. And in heat, darkness is no protection at all. We are about to be able to see the things that have always been able to see nothing of us. Which brings this all the way back to a small spacecraft, crossing a void in 1972, with its detectors listening for impacts that never came. Pioneer 10 went into the belt carrying a 1 in 10 chance of destruction, and came out the other side untouched, having found nothing larger than a grain of coarse sand across 280 million kilometers. At the time, that felt like a reprieve. The wall we had imagined turned out not to exist, but we had been frightened of the wrong thing entirely. The emptiness was never the danger, and it was never the point. The belt is not a barrier, and never was. It is a slow machine that has been grinding for 4.5 billion years, and everything that has ever mattered about it has come from what it sheds rather than what it holds. It is an archive, material assembled across the entire width of the young solar system and filed, unaltered, in the one place nothing ever grew large enough to erase its own history. It is a supply line, permanently loaded, permanently running, aimed at nothing, and pointed inward through our orbit. And it is a verdict still being written, because the same process that pulverized the Yucatan and ended 3/4 of the species on Earth is the process that delivered warm brine, ammonia, amino acids, and the letters of the genetic code to a young planet that had no way of making them for itself. The rock in the museum case and the salt in the Utah clean room are the same story, read from opposite ends. Pioneer 10 is still out there. The last faint signal from it reached Earth in January of 2003, and since then it has continued outward in silence, no longer able to tell us anything. But it already did. It told us that the place we feared was almost entirely empty, and it took us another half-century to understand that the emptiness was carrying everything. For 4.5 billion years, that machine ran with nothing watching it. Collisions, drift, resonance, arrival, over and over, in the dark, unobserved. Every creature that ever lived on this planet stood beneath that same sky and had no way to look up and understand it. The dinosaurs had no word for the thing that was coming, no instrument, no warning, not because they were unlucky, because nothing on Earth could yet see. That changed inside a single human lifetime. The newest thing in the solar system is not a telescope or a spacecraft or a handful of dust sealed in a clean room in Utah. It is attention, a 4 billion-year-old process finally being noticed by soft, short-lived creatures who worked out how to read a rock's birthplace from a smear of clay. And tonight, some of that attention was yours. You spent hours of a finite life understanding the sky above your own house. That is not a small thing. That is the entire difference. Thank you for coming this far with me. If this journey meant something to you, a like and a subscribe are how I know to keep making them. More are coming, quieter ones, stranger ones further out. Sleep well. The sky is being watched now, partly by you. Good night.